Good morning, everybody. How are you folks all doing out there? We finally made it to week 12, haven't we? I'm just going to make sure my recording has started. That seems to be working. Start recording. It's embarrassing when I forget to do my recording because then the video does not get uploaded. Week 12, COMP2300. Who would have thought that we would have gotten here after so many weeks? After much disruption, some dramatic restarting of our teaching methods, but we've made it all the way to the end of this course and all the way to the end of the significant content. Everybody in class now should be working on assignment 3 in some sense. I guess I'll just bring up the assignment 3 page so we don't forget what you were supposed to do. Everyone has their wires. I haven't heard any complaints about wires. There's been a few little discussions online. I'll just get a disco board, sorry. There was a little bit of a discussion about how to get the connectors to go onto the disco boards. And one issue is that, like, when you pay $2 for a set of connectors, maybe they're not the world's greatest ones. They will work, but they can sometimes be a little bit loose, and they particularly don't like to sit on the small pins on your disco board's top. Right, so there's this pin header which goes all the way through the disco board, and you only get a little bit of pin here, so the connectors tend not to grip those very well. If you just connect them on the back, then you get a much better grip, and you get a much better connection. And you might find that sometimes they're a little bit wobbly. That's usually okay, just as long as you can demonstrate that your assignment is working. You will have to just be a little bit careful about the wobbliness when you're testing your sender-receiver code, because if they are wobbling and the connection is a bit loose, you might want to make sure that they're sort of pushed down on your desk or something so that the connection is tight when you're doing that test. Generally, people don't have any issues with these ones, but there can be a few issues, particularly if you're trying to use the little pins on the top. So just try the pins on the bottom if you have issues with that. Everyone seems to be doing some great work with the assignment. There's lots of excellent questions coming up on Piazza. Adam Rollins says that he's working on his assignment in the sense that it's in the queue, which is what I expect everyone will say. It's a very busy week for everyone in the university, week 12. Getting all of your assignments and final assessments in for courses is always a bit crazy. I know that things tend to go in the queue, but just make sure, even if you are queuing up assignment 3, that you have gotten started and that you kind of know what you're going to do. The reason I tell you that is that we're able to help you with the assignment this week. We've got assignment help sessions on Wednesday and Thursday, in the same way that we have for the other 2 assignments in this course. In those times, we'll be here to help. We won't be here on Saturday, Sunday, Monday, on the weekend, on the public holiday on Monday in the ACT. We're not going to be able to help you with your assignment. And on Tuesday, it's our policy not to go into big help sessions on the day the assignment is due. It's just too stressful for everyone involved. So we won't be able to help you much over the weekend and in the day the assignment is due. So that means if you think you might have questions, bring them to us this week, and make sure that you make use of the time where tutors will be here to help you. Of course, if you ask questions on Piazza, you might get a help on the weekend, but we can't guarantee it. So it's about making sure you do a little bit of risk assessment of whether you're going to completely leave your assignment to the weekend. I know that probably people will, but if that's you, then we won't be able to give you much help if you run into trouble, whereas we will this week. Something I particularly want to bring up as a good question would be to make sure you have a bit of a plan for your part 2 in this assignment, and just run it by your tutor this week, either in an assignment help session or at your lab. Because your tutor can give you feedback on whether your assignment 2 idea, your part 2 idea is too crazily hard, just right, or maybe a little bit too simple or too easy. Sometimes we get students coming in saying, oh, I have this part 2 idea which meets the specifications, this should be fine, right? And in some sense, it's fine. You might not fail as long as it works, but the students get a mark and come back and they're like, well, this is not a good mark. I got a terrible mark for this. And afterwards we're like, well, you really did maybe the simplest possible interpretation of what could scrape through the specification. And that certainly is enough to get a mark, but perhaps not the mark someone was looking for. Yep, so Mitchell is just popping on the Teams chat right now. Some very good advice. Prerequisites for doing this assignment is completing labs 9 and 10. The labs aren't there just for fun, they're for learning how to do learning the important concepts and skills that are needed to get the assignment done. So make sure you get into those if you haven't done them yet. Just to remind everybody, final exam details are out, 16th of June. We have a little bit of a discussion happening last week on Piazza in the lecture about this sort of significant final question in the exam. I guess the problem with these exams is that they're completely open book, and it's hard to keep track of exactly what everybody individually knows. So for that reason, there'll be one question in this exam where you really have to do an acceptable job in this question to pass the course, to make sure that I'm confident that it's knowledge that you have about everything in the course, not someone else's knowledge or non-information copied off the internet. This isn't something that's to be really scary. If you do like normal assessment, you have a normal level of seriousness about approaching your assessment tasks, you won't have any problems with this question at all. But in any case, if things go completely wrong with this question, I'll be in touch to make sure that you have the knowledge to get through this course. So it's supposed, just like the hurdle lab, which wasn't really a hurdle this year, it's supposed to be not scary, but it's also supposed to be a little bit scary. So it should be scary enough to make sure that you take your assessment seriously, that you make sure you give this last question in the exam enough time. But it's not something that is a terrifically high bar to pass. It's just the basic normal information and making sure you can express yourself and explain the concepts in this course. So I haven't got a practice quiz ready for you yet, but that will be something that will be available towards the end of this week, and I'm sure people will get right into that after the assignment is done. Okay. Any other crazy questions right now? Otherwise, I might start our farewell tour through all the material. I made a new farewell tour intro logo so that you can keep on top of the course. Keep things interesting in the very last week. Do a new intro animation. Okay. Back to the topics. Now, oops, just getting myself sorted out here. So the whole of this week is revision. We're not doing any new material here. And if something this week is new, then maybe it's not really new, and maybe it got a bit lost in the mix earlier in the course. Things were certainly pretty crazy in the first 4 weeks with the way we were teaching shutting down randomly. So I think that it would be expected that maybe some information got a bit lost. Now, this course has been a heck of a journey. It's been a huge journey through computing topics. I think that this is quite a tough course in that we have to cover a lot of material, and it's like the topic is how computers really work, which is just a huge area. So we're trying to get all of you, and you do very successfully, gain a lot of foundational knowledge in computer organization and architecture. You also gain a lot of foundational knowledge in CPU architectures, operating systems, networks, as well as these quite detailed skills which you've built in understanding how to do assembly programming. And we really ask of you quite a lot of depth in that, in terms of creating significant programs with assembly, being able to discuss your designs, implementations, and analyzing these programs. So it's a big course, it's a big journey through these topics. And just think about where we started when we were just having a look at some digital logic circuits and starting to write just one little instruction on the disco board and calling that a success. So let's just take a step back and try to look at the whole course holistically. So I've got a diagram here of what this course was about. Let's just take a moment to think about this. I think that broadly there are 9 topics in this course, and they go into 3 big areas. So the 3 big areas are like this kind of computing instructions area. I guess you can also call this computer organization. So what is this assembly language thing? How do CPUs actually work? What are they doing to make, to take a line of code and turn that into an action that they execute and produce a result? And that's what we did in that big broad topic. So the 2 main parts were the kind of first three weeks of the course. Digital logic we did in 1 week, and then there was 2 weeks, week 2 and week 3, where we worked on what you can call at a higher level the hardware-software interface. So I want you to have a bit of a think about what that means as we go through. And the 2 topics which we covered there were the 2 different types of operations that are on your disco board: ALU operations and memory. And so we did a lot of learning in those early weeks about how your computer processes instructions and creates actions. We just talked a little bit in those early weeks also about architecture. So this architecture topic kind of cuts across our two big topics here. So we learned like the basic CPU setup, right? Having the ALU, having the memory, having the registers, having the control unit with a decoder and a sequencer, and having flags to help us understand what to do next. So that was our sort of first big topic. And then once we had a handle of how a CPU works and how assembly programming works, we started to think deeply about how to actually get stuff done in assembly. That was the second big task in this course. So I call that the high-level thinking to assembly topic. So in that topic, right, we've got to take everything you know about writing code in Python, in Java, in Haskell, and then say, okay, I've got this code there. I've got an idea of how my program is supposed to work. Now, what am I going to write in assembly to make that happen? So that's why that's how we ended up covering functions. We ended up covering control structures and then data structures. And once we had those 3, I think that many of you will agree that covering these three things, we had a lot of what you need to write almost any significant program directly in assembly code. It may not be quick and it may not be that much fun to write it, but you can do it if you need to. You can do anything you want to in assembly with these building blocks. So this was a pretty exciting part of the course actually, because you were like making big progress each week, doing new things in your labs, and I hope that you really felt that you were getting on top of actually writing code with your disco board, which is quite fun. Then we had this final topic, which is like, how do computers interact with the world, right? We're opening up a few bits of foundational knowledge about larger topics in computing and thinking about how your disco board is going to interface with other things going on. The first one we worked on was the interrupts and asynchronism topic. So does your disco board address sensors? How could you connect a keyboard to it? How could you connect other controllers or other interfaces, other devices through sensors or through direct lines or through potentially networks, which we talked about the week after that. And then what happens when you run multiple programs, this idea of concurrency and asynchronism, which was a really, really important one. And you now have the foundational knowledge in that topic to continue in COMP2300 if you're taking that next semester. We worked on the networks topic so that you would understand, once you connect a disco board to another device, how can you start to describe the connections between those two devices? How can you describe the data which gets sent between? And how could you create your own connections between devices? Then, having opened up this idea of running more than one program on a disco board with the concurrency idea, we talked a bit about operating systems, which was very important as well. So this was one of our foundational topics. You have to understand what the basic roles of an operating system were, what the basic components were, some different design ideas for operating systems, and then some kind of hand-wavy but interesting ideas about how you could implement an operating system on a disco board and what the limitations might be there. And this topic, I guess all of these three topics, or four topics really, going into the architecture one, they give you the start of knowledge which you could then go further in a later course, right? So many of you will take COMP2300 next semester, where you'll go more deeply into asynchronism and concurrency. We have multiple courses that deal with aspects of computer networks. We've got a course on operating systems, the ANU, a third-year course. And in architecture, I'm not sure what you could do, but you could be doing either like high-performance computing courses, or maybe looking at some engineering courses about more to do with computer engineering at higher levels. The final topic which we did last week, this architecture topic, really brought us full circle, right? We were looking at the diagram of a CPU again, and then wondering what advancements could be made in CPU architecture. And the particular one which was very important was, what parts of a CPU can you duplicate or multiply to make it go faster? So we started looking at multiprocessing, when your CPU has multiple parts that are mirrored or doubled or layered up, and somehow you can either run multiple programs at the same time or make your single program go faster with something like pipelining. And we have a few strategies for dealing with that, which we will get to again here. But we ended up with this tour, right? We went this way, hardware-software interface, then functions, control structures, data structures, asynchronism interrupts, networks, operating systems, architecture, and then somehow, when we're looking at architecture, we're touching back at digital logic. So it's really like a big circle of topics, not exactly building up knowledge. And I think that's sometimes how learning works, right? You've got this whole field of computer organization, program execution, And there's all of these different aspects to it. And in this course, we go kind of on a circle around that, all those topics. And potentially, actually, we're sort of doing a spiral, right? We're looking at some topics or some aspects of it multiple times, coming back to that information again, particularly in the hardware-software interface part, where we look at instructions, memory, and how your computer, how your disco board can actually be programmed. Because you ended up looking at this all the time in these other topics and also in your labs and also in your assignments, right? We really hammer this one. Okay, enough about this high-level view. Let's start looking at the topics. First topic, digital logic. What do we start with? Here's a list of the topics in short. I'm doing this for every topic in the course. So we started with Boolean algebra, combinational logic functions, some digital electronics, very, very basic idea of logic gates in digital electronics. We looked at number encodings, and we only look at one in this course, 2's complement. And then I asked you a slightly curveball exam question about 1's complement in the mid-semester to really get you thinking about what the limitations of 2's complement might be. We had a look at the basic components of an arithmetic logic unit in a CPU, which was the idea of a digital logic circuit to add two numbers together, so the half adder, the full adder, and the ripple carry adder. Then we put those together in a very simple arithmetic logic unit with a little decoder to get that ALU to do all of the different bit operations as well as adding, which was kind of cool. And then the finale of that was that simple CPU architecture slide. So let's have a little revise of those topics. So here was the logic gates, right? This was the kind of conclusion of the logic gates chapter, where we were looking at how these could actually turn into bits of your computer, right? So this is where logic goes from just being a maths course to being how your computer actually works, or an engineering course, where you start to write a diagram out for how transistors could be turned into a NAND gate with two inputs and one output. And we had a little demonstration of how then once you have one kind of gate, the special universal gate, the NAND gate, you can then create all the other logic gates which you need, and, not, or, and XOR. So that means that you can create a whole CPU with just one kind of gate. You don't need the other kind of gate. Oh yeah, absolutely. Someone's just mentioned in the chat that should not be combinatorial logic. That's a different thing. Whoops. I was reading it thinking, is that say combinational or combinatorial? Combinational. That was a spelling mistake. Combinatorial logic is a different thing than combinational logic. Whoops. Fix it in post. Fix in post. I say to myself. Whoops. Okay. So we looked at our logic gates, and really we weren't going to do that much with this. We were just having a bit of a tour, learning how these things work together. And the finale of this was putting together logic gates into a simple circuit that could then do some adding for us. So here's our little quiz. How many bits can be added together with this circuit? How long does it take? And where does the final carry bit go? So I'll let someone answer me in the chat. Any quick answers on the talk slides now? So interpreting these kind of diagrams is one of the outcomes of this course, having the knowledge to know what these different gates do and to be able to trace through information through them. We don't ask a huge amount of you in terms of digital logic. It's just foundational knowledge and really specifically trying to get to the point of building this simple ALU and putting it in a CPU. So I've got a few great answers. Just going to grab these on the left-hand screen. So this is a 3-bit adder, that's right. So we've got our inputs here. That's A0, that's the first bit, and that's the first bit for the B number. There's the second bit for the B, third bit for B. So we're going to have two numbers together, A plus B, and each of those is going to be like 011, and that means the O would be A0, oh sorry, that would be A2. This is A1, and that's A0. 101 is going to be B2, B1, B0. And then the answer is going to be S. That's another 3-bit number. S2, S1, whoops, S2, S1, S0. See what people are saying in Teams. So the final carry bit is going to go wherever the C2 line is connected, potentially anywhere. That's exactly right. Oops. So the carry goes this way. There's our 3 bits output. So each of these, this is a full adder here, that's a half adder. The full adder is called the full adder because it's got carry input and carry output, not just carry output. And remember how we had to derive the combinational logic equations to determine what digital logic elements to use there. Full, and that's full 2. So the last question was, how long does this take? There was a few thoughts, and someone said 1 clock cycle. So, but how long is a clock cycle, right? I mean, the answer to how long these things take is a little bit tricky, right? You start to get into deep physics and engineering, because a clock cycle is changeable, right? You can make a clock cycle be as fast or as slow as you like. So how long does it take for this circuit to produce an answer? Gabe says technically it depends on the gate transients. Exactly. So you have to know some information about the physical system here. If we were just thinking about a non-physical model, an abstract model of all of these gates, it takes 0 time, right? There's no time concept involved here. If you have the inputs to an AND gate, then the output is just the same as whatever is instantly calculated from the inputs. There's no concept of time. If we put this into a physical sense and make it out of transistors, then there will be some amount of time after applying a voltage to the inputs of those transistors for the output to settle down to whatever you expect it to be. And so that will take some time that has to be accounted for when creating a CPU. And that time would limit how quick 1 clock cycle could be, and many other factors as well. But moving electrons through a circuit and having transistors settle into an output is not exactly 0 time. It does take some amount of time, and it can certainly be a little bit, it can certainly be tricky to work out what that is. You'd have to get into electronics engineering and physics to understand that stuff. Yeah, so there's a suggestion now from Emma that the bit additions have to work sequentially because of the carry bits. So that's true. I suppose all of these ones don't have to work sequentially. The carry bit just goes through here. It's there. These could all be considered to be one circuit, right? And you don't have to do multiple steps. As long as all of the inputs are set up, then all of the outputs will happen instantly in this big combinational circuit. So it doesn't require sequential logic to do this. You only require combinational logic. I've got some more questions about this stuff in a minute when we get to the sequential logic part, so we'll just leave it for a second. Now, another important idea in this digital logic lecture was the start of number systems, number representation in computers. Now, in this course, we only look at one number representation system, the 2's complement representation for integers. So if we've got a binary register, right, we've got maybe a 4-bit register, there's 4 slots, you can keep 4 binary digits. Then you could count up to the unsigned number 15. That's the maximum, using regular binary representations. Now the 2's complement representation gives us a way to represent negative numbers as well as positive numbers. And the trick here is that it gives us a way to do it so that we can use the same adder, the same ripple carry adder, with the negative numbers and positive numbers without any kinds of change. It's a really clever system. So the idea was we wanted to be able to add one number, supposing positive 42, and another number, negative 42, and end up with what would essentially be 0. And so you could do that with 1's complement, as I hinted at in the exam, by just flipping all the bits here. So you'd end up with, if you flipped all the bits, you would have 1, 1, 0, 1, 0, 1, 0, 1. Then you would end up with 0, zeros, with all zeros in the result here. You wouldn't have the 1 in the carry bit. But then you have some other problems where, for instance, if you take the number 0 and you flip the bits 0, 0, 0, 0, you end up with 1, 1, 1, 1. So you kind of end up with this negative 0, which is going to mess up your arithmetic and cause several other problems where you have to, like, if you want to start counting down, 2, 1, 0, the next number would be negative 0. You have to skip that and get to negative 1. So you have to do some other tricks in your adder to account for that. So we don't use 1's complement. We use 2's complement. And the idea here is that to find the negative answer, we flip all the bits and then we add 1. So we're actually going to end up with, 0. I'll erase that. If I can find my erase button. We're actually going to end up with the flipped bit plus 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. And this means that we end up with the correct answer. Whoops, just trying to do it in my head as we went through. Yeah, that's true. Sorry, Mitchell. Correction, if in 1's complement, if you add a number to its negative, you end up with all 1's, which we count as negative 0. I was just confusing myself. So it is easy to get confused with these things, right? I think that the best strategy to learn these number system ideas is to make sure you've got your head full of a couple of little examples and that you're comfortable with making little diagrams to explain it to yourself, right? So if you can get a method to explain it to yourself, well, when we want 2's complement, we want to get 0 as the output. So we need to find whatever will be the negative representation to give us this 0 and the carried 1. Then if you want to just find a 2's complement version of a number, inverted the number with the minus sign, you just need to flip all the bits and add 1. So it's not very hard to find the 2's complement of a binary number, but explaining the reason why is a little bit tricky. Adam says, does anyone use 1's complement instead of 2's complement? No. I don't think that there are any. Maybe some old mainframe might still use 1's complement. It did have a history where it was in use, but it's not in use in any modern computer as far as I'm aware. Yeah, maybe you could look that one up and answer it on Piazza if you can find a modern computer that does use 1's complement. Okay. Moving along. Then we had a bit of a chat about flip-flops and sequential logic. So we were we're going towards this place where we could start to define how memory works. And we wanted to look at this kind of circuit where you have some kind of feedback loop where the output then produces a new input for the circuit. So once you start to have feedback loops in a digital circuit, right, you've got like what's an SR latch look like? I'll just bring up my slide again on my other screen. SR latch. Oh yeah. Our set reset latch with some NOR gates, NAND gates. Yeah, NAND gates, that's what I thought. I always get the little diagrams mixed up. If I was taking the exam, I would have to make a cheat sheet of all the little diagrams. And if it was an exam where you had to not have any materials, you make like your little cheat sheet more and more like condensed and then throw it away on the way into the exam just to keep that knowledge in your head just for the amount of time you need it. Okay, so we've got NAND and NAND. Once we have, that was S and that was R and that was Q and that was not Q. So once we have this feedback, then to work out what the behavior of this circuit is, we have to know what its past states were. So we need to know like not just time step now, time step 0, but time step -1, what its previous state was. So this means we have to use sequential logic to describe that whole operation. And really we didn't go into too much detail about sequential logic except to know that it must exist and that it's needed to describe circuits that have this kind of feedback. And then we brought you from the SR latch to the flip-flops, which were somewhat more complicated, but let you have, for instance, a clock line to set data and an enable line to enable your bit to be set. And then we had a bit of a think about what the possible uses of flip-flops could be. For instance, making a register, using a flip-flop to store each bit in a register. Other things could be making a counter, for instance. You could use flip-flops kind of in sequence to count through numbers, or making a timer. You could make a flip-flop that is just similar to a counter, but it's just continually adding 1 to itself every time it's clocked. Yeah, so that was flip-flops. Now, I guess the concluding this digital logic topic, one thing I want to make clear or ask you, I guess, is what the difference is between those three logics that we discussed, or three logic topics: Boolean algebra, combinational logic, and sequential logic. So you tell me in the chat what those differences might be. Whoop. And then maybe you could also think about whether we need all three of these things to describe computers, and also whether there might be parts of this digital logic story that are missing from COMP2300. Another few things to think about. Even though, right, my job as a lecturer is to teach you things so you know them, it's also interesting to consider what you don't know, what's missed out of a story in a course. Of course, all courses have a finite number of lectures and a finite number of minutes for which I can yell at you about different bits of knowledge. But knowing these things, it's important to, I guess, see how these things fit into the larger world of topics, and how they might make sense, and what you don't know can be as important as what you do. So the answer so far is just a big question mark. Oh, that's not promising. Haven't had anyone suggesting an answer right now. Maybe I'll start to explain my answer anyway. So, yeah, so Daria's got a really great idea here. Oh yeah, here we go. We've got some good answers now. Combinational logic is only the present input, and sequential logic has that past input as well. That was exactly right. So sequential and combinational. So this is combinational logic, gets you these kind of equations, right? FAB equals something, where something is a Boolean logic sequence, or sorry, a Boolean logic expression. Sequential logic, this is only you know, just right now. Now sequential logic has now and past states. So if you had something in sequential logic, you could have A time A t minus 1, right? B time B t minus 1. So the equation in sequential logic would rely on more time steps of all of these states, all of these inputs, A and B, equals some complicated thing. So, but what about Boolean algebra? Where does that fit into this story? Well, what we've got in combinational logic and sequential logic were expressions with an equal sign, right? We had that kind of logic function, f of something, a, b, c, equals something else. Now, everything on the right-hand side of the equal sign was a logic expression. That would be something like a and b, or not a or b. Okay, so that was a Boolean algebra expression. Now, an algebra is a way of replacing bits of the syntax. It's a way of describing replacement rules. So, you know, not A or B could be replaced by that sort of high level A implies B, higher level statement, which we tend not to use that much. But there are lots of replacement rules in Boolean algebra, De Morgan's rule, and many others. And so the Boolean algebra part was really how to kind of giving us tools to simplify these expressions. Sometimes some of them could get quite crazy. Expression in logic of a combination of symbols with those operations between them. And an algebra gives us a way to replace parts of it, simplify it, make it more complex, pull it apart in different ways. That's what Boolean algebra does. Combinational logic is our way of using, of doing equality expressions, making some kind of function and working out how to find the different Boolean algebra expressions that are equivalent to that function. So we certainly need all three of these things to describe computers, right? Because any Boolean algebra expression, as Adam has correctly said, can be represented as using logic gates. So that one is, well, the logic gates is every mathematician will yell at you for saying we never use A implies B. I am a mathematician, so that was my bachelor's and honours, but we don't use it in the course that often. Yeah, exactly. Shunsu is saying combinational logic has no storage capacity. So we need all three of these things. Sequential logic to deal with storage and like things that happen in between clock cycles on a computer. We need combinational logic to handle storage-less stuff like the ALU operations. And we need Boolean algebra to work out how to handle these symbols. And why do we need to handle these symbols? Well, as we saw in the first lecture, when you start to work out the equation of an adder, if you just do it from the logic perspective, you end up with this crazy equation, which you then need to transfer somehow into digital logic gates. And there might be questions about like what digital logic gates do you want to use? And I said before that often we only use NAND in the computers. That's like the universal gate. So you would want to use Boolean algebra to find ways of replacing in your expressions all of the different logical sequences, all the different logical expressions with stuff that only involves the NAND gate, and then you can transfer it into a circuit. So that's maybe a bit of the story which is a little bit missing from COMP2300 is how to get specifically methods for getting from combinational logic functions and sequential logic functions to circuits. And there are lots of methods for working it out, and you can do simulations and create sort of software-based CPUs and define them all in little programming languages, which we don't do it. Way of encoding first-order logic using logic gates seems a bit difficult. It does seem a bit difficult. I don't know. Go and have a research about that one, Adam. I want to keep moving so we get through a few more topics before I run out of time, which I'm certain to do. CPU architectures, this is the slide we got to. I've talked about this last week a lot, but this is kind of tying in the first week of the course and the last week. The main components of the CPU and what they all do. So it's a challenge for you to find out, to be able to do this. Can you explain what each of these components do and why they're necessary? Given that this is sort of a toy model, right? So not, you know, when engineers make a CPU, are they bound to make it look like exactly like this model? No, they do whatever makes it work best. And they do whatever makes it work with existing software and existing tool chains and existing manufacturing techniques. So there's lots of differences between real CPUs and toy models, but the basic components are all there and they're all working basically in this way. So we'll come back to that later. I'm going to keep moving. Hardware software interface. It's a bit of a weird term because I didn't use this word when we were talking about it in week 2. I was just saying, now we're going to figure out how a computer works. And that's what this really means, right? What is there between, you've got your digital logic on one side, digital logic, and on the other side you've got your high-level programming language. And then there's some kind of wall in between them, or a semi-permeable membrane, where somehow we can get information over to the digital logic side and we get results back into higher level programming. And this is what we're interested in, the interface between the software which you write in high level programming languages and the hardware, or the digital logic and hardware devices that make up a computer. So in short, what instructions look like? We've done that a lot, working out how to directly go from assembly code to a CPU instruction, doing those very difficult and annoying exam questions, I'm sure, where you had to translate it into a binary code. Looking at the status flags, NCZV, looking at all of the ARM v7 instructions, the ALU instructions that don't require memory, looking at the memory instructions then, looking at the branch instructions, and all of the contents of your quick reference card, your little disco board cheat sheet, which I'm sure you're all very familiar with now. So I already talked about this one, but I think it's important to have these kind of high-level explanations ready in your mind. So make sure you think about this question for you. What is the hardware-software interface? Why do we call it this? So make sure that you can describe that question to yourself as part of your revision. Another question that came up in lectures was thinking about why we need both immediate and register versions of some instructions. I guess this was, I'm just going to type the question here. Why do we need both im and reg versions of some instructions? Oh, should have had it in the replies. Delete. I always accidentally post in the wrong place. So maybe when I asked you this question in week 2, not a lot of people in the room really had a good reason to know why we would need both immediate and register versions of some instructions. And for instance, I told everybody in the room that you could do mov R0 12 and put the number 12 in R0. I also told you that you could do mov R3 R4. So you had 2 versions of mov, one to go between 2 registers and one to have a number. But maybe now that you've had a lot of experience, no one's answering my question. Where are all you answerers? Get in there. You can't just be questioners. Now that you've had a lot of experience, I think that you would probably consider it to be fairly impossible to... Oh, I finally got a few answers coming in. Yeah, it's true. So 2 really good answers, one from Emma and one from Robert. Robert was saying if we only had immediate, we wouldn't be able to do much with the information we have. And if we only had the register version, we wouldn't be able to really get data into the program. So you need both in some sense for MOV. And then Emma has said, well, maybe you'll use the register version if you need the result from a previous instruction. That's very true. So we definitely need it, particularly with the MOV result, we need to have some way of getting numbers into the computer, right? You need to be able to load a number in somehow. And of course you know that you can either do it with a MOV, you can also do it with the lit pseudo instruction, which sometimes uses a MOV behind the scenes and sometimes doesn't. So this is our way of kind of directly getting information into the computer, which is obviously necessary. We need to get numbers in somehow. And this one, once you do a few non-trivial programs, you might need to move your information about between registers, so you can save information from getting overwritten by a function, for instance. You can save something for later in a different register. You could put something into one of the special registers like the stack pointer or LR where it has other uses. So we need to have these versions of some instructions, and it sort of saves our memory to be able to remember that there's one instruction that can do kind of both things. A few other thoughts. Yeah, it's annoying that some instructions, as Aggie's saying, it's annoying some instructions don't have an immediate version. So multiplication doesn't. And then you start to feel the pain of no immediate versions of instructions. I was having a little look at, I've got a 6502 computer on my desk, this little toy computer, which I might have time to show you a little demo of today. But that one doesn't have all the immediate instructions, so you're really much more constrained in what you can do. The flags, -0, carry, overflow. Let's go through these ones. So the negative flag, as you all remember, was set when the result of an ALU operation is negative. So if that highest bit in the result register is negative, the negative flag will be set. As long as you are in a instruction that sets flags. And remember that not all instructions set flags, and not all instructions set multiple flags. Okay? And this is a thing which is hard to remember. It's a thing that even lecturers, such as myself, can psych myself out on, as I have done publicly and embarrassingly during this semester. But it's tricky to remember which instructions set which flags. So don't forget the subs, the S suffix, if you want to set flags on a regular ALU operation. The 0 flag is always set if you're setting flags and if the ALU operation's result is 0. So if the result register is all zeros, 0 flag is set. The carry flag is set when the operation has the carry bit set. If the carry out of the operation sort of ends up in the carry bit. So if you are adding two numbers together, which are going to end up overflowing in an unsigned sense, then that is, it'll require 33 bits to represent it. Then the carry bit will be set. And then we have overflow. So really carry is kind of like, it's our node of our flag saying, you're trying to do an unsigned operation and it's gone wrong. So the carry bit is set. That means that your unsigned operation was not exactly successful. The overflow is only for signed operations. So this means that you're trying to do a signed operation and it's gone wrong. The signed operation is not going to be successful. So if you end up at the largest signed integer and you add 1 to that, then your overflow bit will be set. And if you end up with the smallest signed integer and you subtract 1, your overflow bit will be set. How do these work? Well, overflow, we had lots of chats on Piazza about overflow. It's kind of the trickiest one to imagine because you're kind of in a weird place in the range and your intuition is off about how it should work. So the overflow bit is set if this is positive and that's positive and then the result is negative, that is, it's got a 1 in the highest bit, then the overflow is set. And if this is negative, which is negative, negative, or it's the same as doing adds 0 minus 1, and then that is positive, then overflow is set. So if you're adding a positive plus a negative, overflow is never set, as far as I'm aware. Here's waiting for someone on Piazza to tell me I'm wrong, but let's just see what people are talking about in the chat. I guess another hard question. Sorry, I just saw this great question from Mitchell. What about this? Do you think of a way to do around not Man, that would have been a really good exam question, but I've just burned it by by asking in the chat. So, I mean, I've asked you a million questions in practice exams about what flags are set. I don't think we should go into this one right now, but it's good to keep practicing, testing your knowledge and making sure you can generate a instruction which can set any flag. So work out ways of doing those little tests. You had a lot of exercises in the labs, make sure you can do them. We talked a bit about the memory map. This is where we start to, another part of the hardware software interface was how you actually control hardware in your disco board. Where is code stored? It's stored in memory. Where is memory stored? It's stored in memory. How do you control interfaces on your disco board? Through memory. Now you've gotten to this part of the course, you're really, really confident in using these like weird registers up in this area where you're sending information to a register and it ends up with the LED turning on your disco board. Or you send some information to a register and it activates an interrupt on your disco board, or hooks up a pin, or sets that pin to be to trigger an interrupt on a rising edge, for instance. So you now have a lot of experience with the memory map that you didn't before, and maybe you didn't expect to get when we were in week 3. But still an important one to consider. The sort of the last ALU operations was like these shifts and rotates. Logic shift left, logic shift right, arithmetic shifts right, and rotate right. And then the rotate and exchange operation, the mysterious rotate and exchange. So I know that there's like, we can get a couple of extra interpretations of these ones. Of course you need them if you want to just create a bit pattern. Maybe put a 1 in the first lowest bit, then shift that up the number of places you want it to be. But you can also use these ones for doing some kind of multiplies by 2. That's multiplies by 2. For each bit you shift, it's multiplying by 2. This one, if you've got an unsigned number, you can divide it by 2 with each shift to the right. And if you've got a signed number, you can shift it, divide it by 2, signed there. We've got the rotate right, which can sort of move your whole number around and put the lowest bits up at the highest end. And then this slightly weird one will rotate right, take whatever bit was in 0, put that into carry, and then put carry into bit 31. So I haven't ever had a good reason to use RRX in a regular program. I asked the tutors last night, has anyone ever used RRX for anything? And then Benjamin Gray said, do you mean not in an exam? Because obviously it's like only the kind of thing people ask in exams you never use in real life. But Benjamin Gray also thought of a good example where you could use this to divide by 2 if it was, oh no, I've forgotten. If it was unsigned, oh yeah, you can, if you've got something where you end up having a number in carry, so say you've added FFO and FFO together, then you've got something with the carry set to 1, and you can now divide the result by 2, and it will automatically handle putting the carry in. So you can divide a 33-bit number by 2 using that operation, which is handy. Maybe work through that one at home and make sure you can get it to work. Yeah, so the answer, I had this question about, can you think of a way to work around not having any immediate instructions? So some architectures have a 0 register. So it always gives you 0. Always gives you 0. And an instruction to increment a register. So with those two, you could make any number. So good thing for you to do at home, think of a use case for each shift and rotation instruction. Make sure you have all those clear. We talked a bit about load store architecture in week 3, but maybe it wasn't clear what that means. And now it's more clear that you have more experience with them. So in a load store architecture, that's a property of the instruction set. The instructions are either an ALU operation, so they take inputs and save results to registers, only using registers, or a memory operation, so they only save and load information from memory. So the question is what this means for you as a programmer. That's something to consider as you're doing your revision. There are some systems where, for instance, in x86, I think you can have some instructions that will add a number in a register and a number straight from memory. So they're sort of using memory as well in the ALU operations. So they're not load store. So how do we do these loading and storing operations? Well, you're now incredibly experienced, but very simply, you would have an address in a register. You'd get that there somehow. There was our first address in SRAM. It's always been a constant character in this course. And then when we put the brackets around the register, that means we want to consider that to be the address. So loading into R0, whatever it finds at the address in R1, the address noted by R1, and sort of the same but backwards for store. R0's got 42 in it. We're now going to store 42 in that memory address located by R1. And each memory address stores 1 byte of information. 1 byte of information. So it's a byte addressing standard. A few extra operations for your loads and stores. Loading and storing less than 32 bits at a time. Very useful to do as part of your work, particularly when you're storing weird things in memory like characters or half words. It's very common to store things in memory that are shorter than a word, smaller than 32 bits, and you don't necessarily want to have to load in the whole word and then like zero out the information you don't want. So those ones are really handy. Then the specific loading and storing operations for dealing with the stack. Your store multiple decrement before, so it would move the stack pointer down. SP is going to go, if we've got our memory blocks here, right? If we want to store 2 registers, well, I'll make sure each one of these is 1 word, okay? So just take my word for it. SP will be there, or just above it. Store multiple decrement before, it's going to move the stack pointer down to here, and then fill up this information with the contents of 2 registers that we wanted to store. Load multiple and increment after is going to do the reverse operation. Load all of this, and then move the stack pointer up there. When you move the stack pointer around, you never really erase your data. You're just moving the stack pointer. Anything below the stack pointer is considered to be blank. Fair game to be erased in a negative stack. Then the push and pop operations will do almost, actually the same thing, and just give you a little, they only work with SP. These ones you can choose which register you want to be the stack pointer. You could have some stack in some other location in memory. Conditional branching. Oh, there's 1,000,001 kind of condition codes for branches, aren't there? Well, actually just 8. But we tend not to use all of them, but it's a good thing to make sure that your knowledge is thorough on these. All the ones on the cheat sheet are certainly fair game for exam questions. And yeah, they're a little bit tricky to work out what some of these less used ones would be for. So make sure you've got good use cases for each one of these. Oh, we're back at a little stop point. Fun fact from Mitchell, I just want to now read this. The opcode for load multiple and increment after has a position for RS, So if you put the number 13 there, since SP is R13, you get exactly the opcode for pop. What? Mind blown. My goodness. Okay. Wacky. Well, you learn something new every day, don't you? I should note that I started teaching this course in 2019. So I've taught this course 1.5 times, I would say. And some of the tutors have been teaching this course for about 4 years, or 2017, 18, 19, 20, yeah, maybe 3 or 4 times. So there's some tutors here who have a lot of experience with all of the material in this version of COMP2300. I've been involved in teaching a previous version which we didn't use the same material. So we're at a bit of a break point because we've covered now 2 topics. Those ones are done, or tick and tick. Those are pretty weird ticks. They're more like square root signs. Oh well. Let's see what's going on in the chat. There's always more to learn, as Mitchell says. We're now moving into this high-level thinking to assembly topic, which I'll just talk about a little bit before stopping, I think. So functions. Functions are one of the most important topics in this course. Having a good grasp of functions is, I would say it's one of these minimum standards, right? You really need to understand what a function does or what you expect a function to do in order to implement it in assembly. And I think that's actually, just going back to this diagram again, I'll make another big point. To do this part of the circle, right, high level thinking to assembly, I used to think that this involves knowing how to do all of your basic things, functions, data structures, control structures in assembly. That's all there is to it. But now I've started to think that, particularly for students at the stage that many of you are, second year students, maybe some of these things, functions, data structures, and control structures, you might have looked at them a few times in first year. Maybe you've looked at them a bit before in computer science classes in high school. But you might not be completely clear on what you expect from those different control structures. And when you have to do them in assembly, your knowledge about what if then else, what for loops, what functions, and what arrays really mean has to be super solid. Otherwise, your implementation in assembly will be kind of inconsistent, right? So learning about how to do these things in assembly means you have to improve your knowledge about what they mean in high-level programming languages. So it actually sort of plays back into your knowledge that you're building about how to program in a high-level way that you developed a lot in first year, and now you're in second year where we're secretly making you develop that even more. So understanding what a function really should be doing allows you to implement it in assembly. So with functions, we had a lot of topics. We were dealing with the big concept of there and back again. We were dealing with the stack, we were dealing with calling conventions, functions calling themselves, local variables and the stack frame, which was a wild one, relative addressing, that was not so hard, and then passing values, which is a little bit difficult to make that concept precise in assembly. But we had this sort of a high-level view of what a function should be doing, right? F ... or BL, right, in assembly, label name. And it should be taking your program somewhere else, doing a bunch of stuff, having a big battle, killing a dragon, getting some gold, and then coming all the way back again, just as if it had never left. And ideally, your function should be using calling conventions properly, so they should be saving all of the callee save registers when they're off doing their adventure. Over here, all the callee save registers are saved and then they're restored on the way back. And then the caller part of your code is handling all of the callee save registers and then restoring those afterwards so that maybe it's doing a bunch of pushes and a bunch of pops and putting them back the way they were. And really, if your functions are arranged kind of with good discipline in terms of calling conventions, you won't have issues in your code in terms of accidentally overriding registers. But just doing those simple pushes and pops at the right place in your function and the right place in the calling code is sometimes a bit of a challenge, and it can cause some really irritating and difficult bugs. There's your function call there and back again, just what I said. And the call standard, the procedure call standard. Oops, more comments from Adam. It should be a hobbit. Okay, the summary of the standard was this: whatever your calling code is has to save these registers. Whatever your callee code is, whatever is in the function has to save these registers. And then these ones, R12 through R15, are special. IP, SP, LR, PC. So LR and PC are special because they're wired into the CPU in a slightly different way. There's only certain things you can do with them. SP, IP, and then R11 is equal to frame pointer as well, are just general purpose registers. And they have a name, a special name that can be used sometimes, but they are also can be used for anything else. So some people found that if they were storing stuff in R12 or R11, R12 in particular, then functions might accidentally overwrite that data, and they wouldn't find it there when they came back to get it. So be careful about that one. Storing and loading to the stack. We started to look at our offset stores, which were really important. And there were some good questions in the mid-semester exam on that one. Popping values off were looking at like the specific step-by-step way to put this value on the stack, whatever is in R2. So we would have the stack pointer here. That's at our last used address. That's used. And then there's 4 below it, which are unused. So we're going to save R2 there. R2 is going to go in there. And then the second step is to move the stack pointer down. So the stack pointer now points to there. Two-step operation. Just keeping an eye on Teams to make sure I'm doing everything correctly. Then we can do lots of other one-liners for push. We can use this one, the write back version, which with the exclamation point means that it will include the writing back of SP as part of that. We can just use the push operation, and we can use store multiple decrement before operation. The same idea. Then similarly for pop, if we just do it from first principles, first of all, we load whatever we've got here into R3, and then we increment the stack pointer back up 4 places. Why does it have to be 4 places here? Why 4? Well, you remember the addresses are by bytes, and one register is 32 bits, which is 4 bytes. So normally when you do a load, you load 4 bytes at a time, you're storing 4 bytes at a time, and your address is just the first of those bytes that you're loading and storing to or from. And some other one-liners for pop. Push and pop illustrated. We went through this in great detail. I think people ought to have the idea now. Using the stack is not optional when you're programming. The stack is not optional. It's your main way of saving information within a function that you just need for a few minutes. So if you haven't used push and pop in your assignments, now's the time to do it. If you haven't gone through some code to understand how to use the stack, like my examples from the stack week, go back and have a really clear look at that and really get into understanding how to use the stack. It's absolutely crucial as a data structure as a way to store information. It's not complicated. It's basic stuff, not advanced stuff. So we had this, we had an idea, a bit of a thought experiment about how you get information into a function. There was this idea of copy or reference as two modes of doing that. Now, when you're in something like high-level language, for instance, C or Java, it's usually made explicit when you're sending a reference to a function, right? If you're in C, you'll send a pointer to a function as it's your way of giving it some information. When you're in assembly programming, well, it's a little bit more tricky. But the idea of by copy and reference is that if you're sending something a copy, then it's allowed to then that information is stored within the function as a different version or a different representation of that data as it was from the calling code. If you're sending a reference, then both the calling code and the function are operating on the same data. So if the information is going into a function, then we're somehow giving a function a register of information which the calling code is not going to refer to ever again. It's given this data to it completely under its control. If the information is coming out of a function, then the function itself is copying some information to a specific place and not worrying about it ever again. If we're getting information into a function by reference, only input, then perhaps you'd be sending a location in memory or a offset on the stack or something, and the function would only be able to read it, not write it. If you're sending information out by reference, then it would be allowed to write that part. And then more typically, we get kind of this in and out information where a function expects to find something in memory. It's the very same information that the calling code has. The function changes it, and then the calling code just continues using it. Of course, that could potentially lead to some disasters if the function does the wrong thing, then you've lost that data. But it's very common to do things that way. The old function stack frame diagram. How many more frames have I got for? Oh yeah, we'll do one thing next time. Stack frame. This was a bit tricky because you have a lot of colors on this slide, a lot of little squares. But because the stack is this fundamental data structure, fundamental way of storing knowledge, we use it all the time when we're doing function calls to keep track of all the important information that a function is using. And specifically for storing things like local variables. That's typically stored in the stack. So we could have this diagram of a function call. This would be like everything that's not in the function in the stack. That's just when you call your main code in the program, it has some global variables. But as soon as you call a function call, it will store its parameters, store its return address, save the callee saved registers, and then save its own local variables onto the stack so that it can access them. And we proved that when we were looking at the compiler explorer online, the Godbolt compiler explorer, because it was really clear that when you put local variables in a function in C, if you have unoptimized code, the first thing that the compiler does is set up space on the stack to store those local variables, so it doesn't have to store them in registers. And then whenever it needs that information, it can go back in the stack and find it. Now this is where we had this idea of a stack frame. So everything here could be kind of called, that's the frame of this function. And the stack frame is the part of the stack which is all the important information stored by a particular function. And it usually has this kind of standard structure, right? Because all of your functions would be compiled by the same compiler. They all have the same or a similar layout, even though these could be variable, right? One function could have a different size of local variables. They could have different sized parameters. Probably the return address is always the same, just one register. So we would often have a thing called a frame pointer, which each function would set up. It would set up the frame pointer to point to the start of the stack frame, so that if it wants to get the return address, it can know that that's at like frame pointer +8 or something. The problem is that during this function, the stack pointer might continue going down from other functions or moving around, depending on what we're doing with local variables. So it will be very difficult to rely on the stack pointer to know where the return address is. That's why you use the frame pointer to do that, which you then store in R11. And then we would know there's a bit of information about the interprocedure call scratch register. It's a bit tricky to work out, but we'll get back to that in a minute. Once you start using functions to call other functions, then you end up with all these stack frames. And the frame pointer in R11, that's actually a callee save register, right? Yeah, so this one's going to have a stack pointer. It calls a function. Then this function in the middle is storing the old frame pointer. Then it makes its new frame pointer somewhere in here, works it out at some point. Then the old frame pointer gets stored in callee save resources. So we're always storing that information as we go down in our function. And the stack ends up with this sort of layered structure with the stack frame from each function which has been called. And of course, when you're doing a big program, you'll end up having functions calling functions, calling functions, calling functions as you go along. There was a bit of a discussion. I'm just going to keep going. I think everyone's excited to revise this morning, so we'll go a little bit longer today. Mitchell was saying interprocedure call scratch register. This is about R12. What is R12 IP? Now, it's not typically used very much. I think unless you're compiling code, it's not used a lot. Oh, that's interesting. Apparently this is used as a scratch register when doing a really long branch. Since branch distance is limited, you can store an intermediary branch destination in R12. Huh. Good to know. That's the kind of thing which you typically wouldn't need to do in this course, because you're not writing huge programs, you're not linking lots of programs together to go move in different parts of memory. So your branch destinations are not very far away. Cool. Now the last function topic was to work out how to do recursive functions in assembly. And I gave you this demo of the factorial function. You have to do all the same stuff in recursive functions in assembly as you do in high-level programming languages, except, just as I said before, when you're doing it in assembly, in order to be successful, you have to be really super sure about how a recursive function should be structured in order to get it right. So in this one, just going through this code on the blackboard, there's the factorial function, assume the input's in R1. What's going on in Teams? Okay, more information about R12. Oops. So the first thing we do at the start of our function is push LR. Now I could, of course, push all of my other callee save registers, but I haven't bothered to in this code, so naughty me. Should have R4, R11 in there, and then I should have R4, R11. Okay, now I'm safe. I've saved all my call E save registers. Okay, so if we want to do a factorial function, that is like 2 factorial equals 2 times 1, the first thing we want to do is, this one actually doesn't handle 0, I think. First thing I want to do is handle the base case. So I'm going to compare R1 to 1. And I said, if it's equal to 1, then I go to the base case. I could have done if it's equal to 1 or 0, then go to the base case, but I've just done 1, so it's not going to work for 0 in this function, so it's wrong. Lecturer doing something wrong, imagine that. Now we're in the base case. If we've got 1 in R1, we move 1 into R0, and then we leave the function. This is return. If we're not in the base case, so if we're at some number which is greater than 1, it could be 2, it could be 3, but let's just say it's 2, then we're going to need to do something else. So I want to do, first of all, I'm going to save my information which is in the caller save register. I want R1 to be saved for later, so I'm going to push that right now. And then I'm going to subtract one from R1 so that I've got my new input for my factorial function. Then I'm going to call the factorial function on n-1. So that's going to be doing fact1. Okay? Now fact1, as we know, we just proved it, fact1 will return 0. So that's going to leave R0 equals 0. So now I can pop my original R1, sorry, it returns 1, duh. Pop R1 back into R1, so now R1 equals 2. And now we can do a multiplication, calculate factorial n-1 times n. R0 times R1 goes in R0, so now R0 equals 2 times 1 equals 2. And then we go to the continue code and return. Whoops. So it works. Now when I have to write a recursive function in assembly programming, the first thing I do is work out what's the base case. So if we're doing our factorial function, the base case is n equals 1, or n less than 1 greater than or equal to 0. That's the base case. Then I want to do the recursive case, which is fact n. So this means that the output is 0. Output's 1, sorry. Recursive case, fact n, then the output is fact n-1 times n. So if I can kind of set this out in the base case and the recursive case, work out how to implement that, then the trick is to make sure that I don't overwrite my input number, my parameters for the function. And in this case, I've done the right thing with pushing and popping and making sure I save my caller save registers that I'm using. I don't have to save ones I'm not using, so unless I wanted to go over the top, but that's what I've done, just saved R1, and that should help us. So I'm not sure, looking at all this, this is kind of crazy, isn't it? Working on a few recursive functions would be a good revision task. You can also look back at the labs where you were looking at functions. There's a recursive function exercise there to do. Make sure you know how to do it. Okay, I'm going to stop here and not look at control structures. But I'm actually going to do another 5 minutes. 5 minutes of something different and fun. So people are probably left to go to their other lectures or whatever, but just to remember what we were doing. Oh, my camera turned off. Really? Come on, turn on. Oh, that seems bad. Okay. Is that going to get anywhere? I'm desperately trying to turn auto off on my GoPro, but it won't do it. Okay, I'll just show you with the regular camera. Back to this one. Actually, I'll make myself big for a minute. So I've got this little computer, which I talked a little bit about last time. So this is a toy computer, but it's a model of the first Apple computer that Steve Jobs and Steve Wozniak made in the 70s. And it's interesting because it uses this CPU called the 6502, which is a famous 8-bit CPU from the 70s. And would you believe it, the 6502 is still in production today. You can buy this CPU, a new version of the 6502. They actually had there's one sort of modern revision which includes a few more little features, but it's still compatible with the old code. And they're still used in things. There's still 6502 code that's created. Whoops, the gray, I was getting, it's invisible. That's hilarious. Whoa, yeah. So where's the 6502 on this chip, on this board? Well, there it is. And this person, I've forgotten the guy's name who made this, but it's sort of a kit that you could buy with a 6502. It's got some memory there. It's got some ROM here for the program and the little pre-built programs. These two extra ICs are just contain some logic gates. All they have is NAND gates, I think. 4 NAND gates in each one, just to do a little bit of tricky switching between the RAM and ROM, depending on what address is selected by the CPU. And this chip here is for giving you some two sort of peripheral input and outputs, switching between them. It's called a peripheral interface adapter. And then this parallax processor helps sort of manage the serial input, output. It does a video signal, which I never use, and handles keyboard input, which I never use. The way I use this computer is just to connect to it over serial with this USB to serial UART adapter. So I'll just turn it on, and then we'll have a go at running a little program on the 6502, which I think is just for interest's sake is cool. So what would computing be like, right, if we were going to do this course in 1977 instead of today? Well, first of all, I wouldn't be able to give you a computer for free because it would be too expensive. The Apple I original was like $600 US, and that was just the board. And then some years later, they came out with the Apple II, which was also a 6502 computer, and that would have been quite expensive for an individual person to buy, but doable. They were personal computers. People really got into them, and Apple IIs were still around for many years. And I remember when I was in primary school, they still had Apple IIs, but at that time they were considered to be old. We don't use the Apple IIs, they're too old, but they were still there. Now, to get this computer started, I actually have to physically hit the reset button, and then I get this little backslash. That's how I know it's working. Now, what have I got here? I've got a cursor. I can now send text to the board and have it send text back to me. So it's sort of an interface of some sort. It's not really an operating system. This computer is running a monitor program, which is just giving me an interface to let me start other programs or test some other things on the computer. And the particular monitor is called the WOZ monitor because this guy, Steve Wozniak, wrote it. Now, what can you do in the WOZ monitor? Well, you can look at memory, right? If I want to look at what memory is in 0300, that address in memory, 4 bytes addressing for memory, there's 16-bit memory addressing in this computer. Now I know that that's got a 55 in it. if I want to see what's in 0301, it's also got a 55 in it. In fact, I think a lot of things have 55 in it. I can look at a bunch of memory together, 32F. So that'll print out a memory range. I can set some memory if I want to, so I might go 300 colon FFEEDD. So I'm going to set 3 bytes of memory using the WOS monitor. Just tells me the first byte. I'm just going to go check I might put myself on the left-hand side. I'll just check what's in that memory again. Oh, I made a mistake. You can't make mistakes in serial. Now, once you've tapped it in, it gets sent. It's sending every character I press as I do it before the enter is pressed. I think I've fixed my head now. Left-hand side should be right. Yeah, now I'm right. So 0300 dot 0303. So I overwrote that first FF I put in there, but the EEDD and 55 is still there. So how about entering a program? Well, I've got one here in my other screen. Well, maybe I could make the text bigger. Oh well. Here's a little program. I just got this out of the manual from the replica one. I don't have that many programs that I've tested with it. It's just a fun thing to try out. But they said, well, take this program and enter this in. So I'll just try it now. Enter in these 16 bytes or so. 0300 colon A9 space 0 space AA space 20 space EF space FF space E8 space 8A space 4C space 2 space 3. A9, O, AA, 20, EF, FF, E8, 8A, 4C, 2, 3. So I'm just entering in the machine code for a program, right? Putting it straight in memory. Like imagine if you could do this in Windows, right? Just say, open a window and say, show me all the memory, please, and now change these ones. I want to start a program. So it's quite a different way of operating a computer, right, than we're used to. Okay, so that's done. And now what I want to do is just, maybe I'll view the program, 300.30A. So that's my program all written into memory. And if I want to run it, I just tell the computer to run the program with the R command to run the program starting at that location in memory. So it's basically just going to do a branch to that memory location. And this little program, all it does is spit out the alphabet. And how can I stop it? I have to press the reset button on the computer. That's the only way to stop it. I was interested in how this program works, so I just disassembled it using a disassembler online. And I've got my code here for it. So you can see that the first instruction, that's the only one I knew by heart in 60502 assembly, which was load. That loads 0, and it loads it into one register called A, which is the accumulator. So whenever you've got the result of an operation and you want, then you have to use the A register. You can't just use any register. In fact, I think there's only 3 registers on the 6502. There's A, there's X and Y. A is the accumulator, that is the result of everything. And X and Y you can use to store information. So maybe someone will tell me I'm wrong and there's other registers, but we'll find out. So A900, we're going to put, it's like doing mov A0. Then AA, that instruction is transfer A to X, transfer ACK to X. Then I'm going to do this 20, which is like a branch to this subroutine in EFFF. Or FFEF, sorry, it's in Little Endian, FFEF. Now, FFEF, that subroutine isn't defined here. That's actually included in the WOS monitor. And that subroutine prints whatever character is in ACK. So I've got a character now, or a number, 1 byte in ACK, and that will be printed out as an ASCII character. So that does the printing here, printing it to screen. Then when that function returns, I increment what I've got in x, I transfer x to ACK, and I jump back to 0302, 4C 0203. So this is not like branches, like branch with link actually, BL to go to a function. And this is regular branch to 0302, which is here. So then we start that process again. So there you go, one very simple program in 6502 assembly. It's a little bit more more frustrating to work with than ARM assembly, isn't it? Because you would have to, if you wanted to make a significant program here, you'd be forever moving things between X and Y and A. As you get a result, put it into X, get a result, put it into Y. Get something in X, put it back in memory. Get something in Y, put it back in memory. So what else can you do with this machine? I'll just reset it again, make sure I'm reset. When most people used machines in this era, they didn't program in assembly, although they could. That was perfectly possible, just to enter the machine code and hand assemble things, right, on paper. But you'd also use the, oh, something's gone wrong here. Where's my keyboard gone? That's odd. Does it work here? Yes. I'll just quit that and start again. Close terminal. I guess what I wanted to show you, which I will in a second, reboot that. I don't know, it's a toy computer, it's not supposed to work all the time. Screen/dev/tty USB 0 9600, just initializing a serial connection. No, it doesn't work. Screen R. Kill that one, start again. Oh, it's really messed it up. Anyway, I can also show you the basic programming language which works on this board. Maybe I can show you that on Friday if we have 2 minutes, but of course we're busy doing the tour through all the topics, so really it's quite a busy week with a lot of interesting questions. Does anyone have any more questions before I leave us for the day on any topic? Any final questions for the day? That's weird. Oh, I can get back into it. I'll wait and see if there's any final question, but I'll show you how to get into BASIC. We need to know where the BASIC interpreter is located in memory, which is E000, and then we need to run that. So type EOOR. Okay, now we're in BASIC, and we've got a prompt actually. So we can start looking at writing a BASIC program. So if you wanted to write a BASIC program, you had to enter it in line by line. Hello world. So I've got 2 lines in my program, and now I can run it, and it does it. Isn't that cool? So I think I can now go the old go to go to 10. This is like the everyone's first dumbest BASIC program. And it keeps doing it forever, which is very silly, until I reset the computer. I'm back. So this kind of computer really is like this kind of programming language in BASIC is sort of what people were going for with Python, right? They wanted a programming language which was easier to distribute, everyone would have access to it, and somewhat like more broad use, so you could use it for any topic. People used to use BASIC for any kind of little tasks that they might want to write a small program for, and then it kind of went out of fashion for some time in the 90s. Haven't been any questions lately, so I guess I can wrap it up. And I'll catch you all on Friday. Work hard this week. I know it's a big one dealing with week 12, but try to have some fun with your assignments, do some creative stuff, and I'll catch you folks on Friday.